So I want to walk through the kinematics equations and calculus and sort of derive the equations and go into some of the fundamental calculus behind it. Some of this was developed by Leibniz, some of it was developed by Newton. They sort of kind of came up with that at the same time. And so in a way, they're both credited for it. So when I look at something that is at a constant position, maybe it is my TV. If I'm watching TV, it's 2 meters away from me and while I'm sitting on the couch. Well, I'm not moving, the TV is not moving, and so that position is going to be a flat line straight away from me. Because neither of us are moving, our velocity or the velocity of the TV is going to be zero. It will also be a flat line. And the acceleration is going to be zero also because remember, acceleration is the change in velocity. So if the velocity is not changing, then there is no acceleration. Now, let's say we're dealing with something at a constant velocity. Maybe I am riding my car down Main Street going 25 miles per hour at a constant speed. Well, that means that this graph, the velocity graph, is going to be a flat line because I'm not changing how fast I'm going. It's 25 miles per hour. My acceleration then, because the velocity is not changing, my acceleration then is going to be zero. And you can think that because I'm going 25 miles per hour, then every hour I'm going to go another 25 miles, which is going to give me a nice diagonal line here. So after 1 hour, I'll have traveled 25 miles. After 2 hours, I'll have traveled 50 miles. After 3 hours, I'll have traveled 75 miles. And so that's why I get this really nice diagonal line. When we talk about the third one then, constant acceleration, maybe I take and I stand on top of the tallest building in the world. I take this really, really heavy weight and I drop it. That weight is going to fall towards the center of the earth at a constant 10 meters per second squared. So that means every second it's going to get 10 meters per second faster. That's a constant acceleration. Now, because it's getting 10 meters per second faster every second, just like the constant velocity graph, the position increased evenly. My velocity is going to increase evenly here. Every second, I'm going to get 10 meters per second faster. Well, if I'm getting faster every second, that means that the distance that I can cover every second is going to get bigger and bigger and bigger and bigger, and I end up with this exponential curve for my position graph of the constant acceleration. Now, let's take a look at the constant velocity one. If we look at the position, this is the equation of, or it's the shape of a line, which means that I can use the equation y equals mx plus b in order to describe that line. If this is position, then this graph is going to be the position, the x displacement that it covered in a certain amount of time. So I can replace the x variable with my time, and I can replace the y variable with my position. Then remember that the y-intercept is going to be the b value, which will be whatever the initial x value is. And when I talk about slope, well, what is a slope when I take a position divided by time? So if I take x divided by t, isn't that really just the velocity? So I end up with an equation that says x equals vt plus x, the initial x velocity. So then I can say that my final position is going to be the velocity times the time plus whatever my initial position was. Now, 9 times out of 10, we'll say, hey, our initial position was 0. And that's where we end up with this distance equals rate times time, or position equals velocity times time. So with no acceleration, the distance is equal to the speed times the time. And notice that the slope of that position time graph is the velocity. Now, let's take that and look at the next one down, the constant acceleration. When we look at that, our line goes with the velocity graph. So again, we can look at the y equals mx plus b. And on a velocity time graph, our y-axis is the velocity, our x-axis is the time, which means that the y value is going to be the velocity, the x value is going to be the time. Remember that the b is going to be the y-intercept, which in this case has to be whatever the initial velocity is. And then when I take and find the slope, that slope has to be velocity divided by time. What is velocity divided by time? Yeah, you got it. It's the graph to the right, just like the position divided by time is the velocity. Velocity divided by time is the acceleration, and that's going to give me a Vf equals At plus Vi. Now, did you notice that that is one of our kinematic equations? Vf equals Vi plus At. It comes straight from that constant acceleration graph that we have there. Now, let's look at the position graph. If this is a quadratic, then doesn't it really describe ax squared plus bx plus c? And again, we can play the same games that we had here, where the y-axis is the position, x, the x-axis is the time. I can substitute in the position for the y-axis. I can substitute in my initial y value, which is going to be the constant at the end, so it'll be the x initial, and then I can put in the t's for all my x's because that's what's on the x-axis. And if we do a little bit of math magic here, which will make sense a little bit later, then we're adding the 1/2 at squared plus vit plus x. And notice again that that equation is also one of the other kinematic equations that we have. Now, when Newton had these, he said, okay, this is really interesting. However, one of the hard things for me to measure is time, because we're talking the 1700s, we're dealing with hourglasses. It's not like they had stopwatches to do. So if I take x equals vit plus 1/2 at squared, and I take the other equation, vf equals vi plus at, and I want to get rid of time then. So I'm going to solve this second equation for time and say vf minus vi all over a is equal to t. And then plug this guy back in for my time. So I can say x equals vi times vf minus vi all over a plus 1/2 of a times vf minus vi over a squared. So here we go, some simple math. vf vi minus vi squared all over a plus 1/2 of, and one of our a's will square and we'll get rid of that. So I'll have all over a here. And then in the top, I'm going to have vf squared minus vi squared. So I'll vf minus vi all squared. So vf squared minus 2vf vi plus vi squared. So I can take this then and get rid of my a's, take them to the other side and do ax. That'll get rid of the a's. I can multiply everything by 2 to get rid of that. So 2 here and times this by 2. So I have 2vf vi minus 2vi squared plus vf squared minus 2vf vi plus vi squared. And notice that we have like terms. These two terms are the same, they cancel out. And whenever I look at these two terms, they will become vf squared minus minus vi squared equals 2ax. So if I simplify that, then I can take and do vf squared equals vi squared plus 2ax. And notice that that is the third equation that we have from Newton's laws. Now to move on to the side that it keeps wanting to bounce to. So if I look at this one then, going back, a key idea is that the slope of the xt graph is the velocity, and the slope of the vt graph is the acceleration. Now, what happens then if I don't have a straight line? So maybe my position graph is this curve. If I find the slope of these two lines, then I'm really looking at the change in position over the change in time. And because we're dealing with the beginning to the end, it gives us an average velocity. But what if we want to find out the velocity at a specific point? So maybe I pick a point right here and I say, hey, I want to know how fast I'm going right at that point. Well, when I get down to that point, then I have another line that's getting closer to it here. I have another line that's getting closer to it here, another line that's getting closer to it here. And eventually I get to the point where I have only one line that is touching the original graph, and that one line is tangent to the surface at that point. But at that point, my time is 0, and so I end up with a problem there. So as the time approaches 0, the slope becomes the tangent line and the velocity becomes the velocity in that instant. And that is really what a derivative is. A derivative is the slope of the tangent line. And if you can keep that in your mind, anytime we're talking derivatives, we're really talking about a slope. A derivative is a slope. So if I take, for those of you who are in calculus, if I take to find the velocity, it's the limit as that denominator approaches 0 of the change in the position, or dx dt. Now, what do you think that the derivative of the velocity versus time graph is? So if I'm taking velocity divided by time, then you got it. As I take the limit of the velocity divided by time, I'm going to get the acceleration, or the graph to the right of the velocity. So key idea here, the slope of the position time graph is velocity, and that's really the derivative. The derivative of the position time graph is velocity, and the slope of the velocity time graph is the acceleration, or the derivative of the velocity time graph is the acceleration. So an example on derivatives, a quick how-to. A ball's position is described by the following equations: x equals t squared plus, so find the ball's velocity at 2 seconds. When I do that, I can take the derivative of the position to get the velocity. So to find the derivative, what you're going to do is take the value of the exponent multiplies the coefficient. So if this is my equation, t squared, then I'm going to take and shift my 2 down into the front, and that's really where this guy came from. Then the exponent drops by a power of 1, so I take 2 minus 1, and that's where I get the 1 from here. And then I can simplify that just to say 2t. So I'm taking my exponent, times it into the front, drop the power by 1. Multiply the exponent times the coefficient, drop the power by 1, and that's how you end up with that. So then specifically at 2 seconds, I can plug in 2 for my time and get the 4 for the velocity. Now, just a keynote, the derivative of a constant is 0. So if there's a constant here, it doesn't matter about exponents or anything. The derivative is automatically 0. So you try. Pause the video, see if you can figure this out. Okay, now that you paused it, or maybe you didn't, if I take this, remember what I'm doing is I'm taking the exponent, multiplying it by the coefficient, and then dropping the power by 1. So in this case, I'm going to take my 3, multiply it by the 4, and then drop the power by 1. So I would have 3 times the 4, drop the power by 1 to be 2. Now in the next term, I'm going to take the 2 times the half, drop the power by 1. Then I can imagine that the 6 has a 1 as an exponent, the time, the t has a 1. I'm going to multiply the 1 times the 6, and if I drop t to the 0, remember that anything to the 0 power is 1. And then what's the derivative of a constant again? The derivative is 0. And so my final equation, if I simplify that, 3 times 4 is 12, t squared. The 2 times the half becomes 1, and then the t to the 1, I don't have to write the 1 anymore, and then the 6, and that's going to be the value of that. So x equals 12 t squared. And this, I'm sorry, I have a typo here. This is not going to be the position anymore. It's going to be the velocity, because remember that the derivative of the position is the velocity. So a physics example, a book falls from the ceiling with the following equation describing its position. X is negative 4.9 t squared minus 3t plus 2. Now, a couple different things you can pull from this. We can look at this automatically and say, hey, when I look at a position at a constant acceleration that is a quadratic, remember it sort of follows this 1/2 at squared, 1/2 at squared plus VIT plus the original position. So I know that because this is plus 2, that is really my initial position. I'm 2 meters above the ground. I also know that this negative 3 coefficient is telling me the initial velocity. The initial velocity is negative 3 meters per second. And then I know that the negative 4.9 is 1/2 of the acceleration. So if I multiply that by 2, I get 9.8, which is the acceleration of gravity in the metric system. So find the book's position at 0.653 seconds. So if I'm looking at the position equation, all I have to do is put in 0.653 into that position equation and then solve to get that the final position is going to be a negative 2.05 meters. Now to find the book's velocity, remember that if I have a position equation to find velocity, I'm really taking the derivative. So the velocity is the derivative of the position equation with respect to time. So I'm going to take and do the 2 times the coefficient and drop the power by 1. Remember that t to the 1, I'm going to take 1 times the -3, and then this becomes t to the 0 when I drop it by 1, and the constant is 0. And so I get a 2 times -4.9 is -9.8t, and then a -3. Now notice that this follows the equation that is VF equals VI plus AT, right? So the A is the -9.8, which we talked about up here, and the VI is the -3, which we also talked about up there. And then if we want to find it at a specific time, we can plug the time in and then solve for what that is. So it's going to have a velocity of negative 9.4 meters per second at 0.63 seconds. Now, how do we find acceleration then? Remember that acceleration is the derivative of the velocity with respect to time. So I'm going to take this new equation here that I have for velocity and take the derivative of it. So the derivative, I'm going to take the 1 power times it by the front, drop this down to 0, so that will go away. And then the derivative of a constant is 0, and I'm left with an acceleration that is negative 9.8 meters per second squared. So hopefully that gives you a little bit to ponder on the calculus and the kinematics and how these fit together. And we'll talk more as we study these more. Oh yeah, one more thing. This is sort of the bonus feature or the extra level. If the slope, which is y over x, means something, then surely y times x must mean something also. So if we look at the constant velocity graphs again, remember this is position, this is velocity, this is acceleration, and each of these x-axes are time. So if I look at the velocity one and I say, hey, if I imagine there being a line here, I stop at some certain specific time, then couldn't I take the velocity times time and that represents something? Well, if I specifically look at the units, maybe I say this is meters per second times seconds, my seconds will cancel out and I'm left with meters. Isn't that going to be just the position? So if the slope tells us the graph to the right, so the slope of the position is the velocity. The slope of the velocity is the acceleration. So this is the slope, and this is the slope. Then whenever we do the area under the curve, the area of the graph is really telling us the graph to the left because this is the position. So the area of the velocity graph is going to be the position. And you can think that the acceleration, if this were a line that's up here, then the area of that's going to be a times t, and acceleration times time is going to give us the velocity. And hey, guess what that represents? That is going to represent, if I ever get there, it's going to represent an integral. And so that's really where Newton and Leibniz got to this, was they said, hey, all of these graphs, these are very easy graphs to find the areas under. But what happens if I have a graph that looks like this, where I have to figure out what the area is under? And that's when they started breaking it down and saying, well, hey, I can draw these lines here, and I can find the area of these rectangles that are underneath that. Well, if I make this line get closer, then I have another rectangle and I've added that area. If I do this, then I have another rectangle and I've added that area. Well, what if I make these lines so close together that I don't have any of these blank spaces that are sort of the goofy ones? And that's really where we came up with what a integral is. So major ideas. X versus t graph, the slope is the derivative. V versus t graph, the slope is the derivative, and it gives you the acceleration. And the integral is the area under the curve is the displacement. So go the other way. On an A versus t graph, the integral or the area under the curve is the velocity. So there are always two parts of the graph that we can look at. That the dividing the axes will give us the slope, which is a derivative, and multiplying the axes will give us the area under the curve, which is the integral.